All right, welcome back to Physics 221. This is chapter 40, one-dimensional quantum mechanics. This is the last chapter on quantum mechanics. This is all math, and this is a tough chapter, so beware. But the good news is the next chapter is nuclear physics, which is actually chapter 42. And nuclear physics is fun and it's not so difficult. And then we'll do chapter 41, atomic physics, but we'll skip most of it. You should have received a handout. It's called Solving the Schrodinger Equation. It just shows all the steps of what I'm going to do on the board today. I want you to have this with you when you're watching this so you can spend most of your time paying attention and learning rather than writing things down. So we're going to introduce the Schrodinger equation as the law of quantum mechanics. Last chapter when we talked about the wave function, we talked about the importance of a wave function and what it's used for and all that, but we said, how do you get it? So this chapter we're going to learn how you obtain the wave function. You obtain the wave function by solving the Schrodinger equation. All right, so to recognize that solutions of the Schrodinger equation gives the allowed energies and wave functions for a physical situation that is modeled by the potential energy function u, x. We're going to interpret wave functions and energy levels, and we're going to understand quantum phenomena such as bonding and tunneling. So I don't know if we're going to do much we won't do much on bonding, but we're going to do a lot on tunneling. Tunneling is completely impossible according to classical physics, but it happens. So it's totally a quantum phenomena. All right, so we're going to start off nice and easy. So this is the baby version of the Schrodinger equation. And it's baby version because it's one-dimensional, it's non-relativistic, and it's time independent. Now there's actually a story behind this. So years ago, when I was teaching this, Physics 221, one of the students, his wife was in a hospital having a baby, and so the student brought his physics book and was studying like a good student after the child was born. Okay. All right, let's see. Now, this is important. We're going to talk, I'm just mentioning it now, and we're going to use it near the end of the chapter. So Schrodinger, he's a physicist, right? So when he was developing this equation, which became known as the Schrodinger equation, he wanted to find an equation such that the wavelength of the wave function was equal to the de Broglie wavelength, which again is h over p or h over mv. So that was part of his motivation, and we'll use it. Okay, now let's get back to the baby Schrodinger equation. Oops. Back. Okay. So notice, so there's the wave function, mass, h bar squared. Notice it depends on energy, right? Newtonian mechanics forces, F equals ma and all that. So this is energy. So it's different, it's different. So let's multiply this out and see what we come up with. So E is the total energy, U is potential energy. Well, that means that this mess is kinetic energy. So what do you think of that? Right? So that's the kinetic energy in quantum mechanics. All right? And you can see it depends on the wave function. All right? Okay. So really, in order to solve the Schrodinger equation, you have to know what the potential energy is. And see, every different physical situation will have a different potential energy. So this is really central to solving the Schrodinger equation, figuring out which potential energy to use, and then it's just math. Just math. Okay, so I just want to run through 3 examples of different potential energy functions. Oops, I'm not supposed to see that yet. So, come on. Okay. Okay, so I've stressed this in the past, if you're going to come up with a physical theory that works with the atoms and the elements, you're going to choose the easiest one first, right? Hydrogen. Well, of course. Well, we'll see about that. So here's a hydrogen atom, proton orbiting by electron. And in Physics 220, we learned that this is the potential energy function between two charge objects separated by a distance r. The E is the charge of the electron or the charge of the proton, minus E squared over 4 pi epsilon 0 r. Epsilon 0 is, again, just a constant you find a lot with electricity and magnetism. Now, this is a three-dimensional object, right? And so it's really easier. You'd be crazy to do this with x, y, and z. You really want to do it with spherical coordinates. So if you do that with spherical coordinates, you get this. And remember, this is the easiest element, right? Hydrogen. So you get this differential equation. Well, that's incredibly complicated. You don't do it most of the time until you're in graduate school. So forget it. We're not doing it. All right. So here, hydrogen bromide. So it's a molecule, right? Hydrogen bromide. And so here's the hydrogen, here's the bromine. So this has 80 times the mass of that. Okay? Well, you know, because this has the mass so much greater than this, and you know, it's attached, or whatever you want to call it, by a molecular bond. Well, how do we always model things like that? We always model things like that, like this, right? So here's the bromine, here's the spring, which is the molecular bond, and here's the little tiny hydrogen, okay? So we're going to assume that this is stationary, right? Because it's so much more massive than that. All right, so what's the potential energy for something held onto something else by a spring? Well, we've done this a million times. It's just 1/2 kx squared. And that's one-dimensional, you know. People in Physics 220 have worked with that, simple harmonic motion. So we're going to do it, right? We're going to solve the Schrodinger equation later on with that potential energy function. All right, our third case is this. So what we're going to do, we're going to come up with a simple model of the nucleus. And we're just going to model it as consisting of free protons and free neutrons. So we're going to assume that they don't interact with each other at all. And there's incredibly strong nuclear forces which prevents the protons and the neutrons from leaving the nucleus. Now, when we do nuclear physics, we're going to learn that this is a horrible assumption. The neutrons and the protons do, in fact, interact. But just to keep things simple for now, again, this is just a model, we're going to say that the protons and the neutrons do not interact at all. Okay? And they can never, ever leave the nucleus because of the strong nuclear forces. And that's not even true either. Okay, so here, so this is the potential energy function for something like this. So basically, the potential energy, all right, so the neutrons and protons are stuck within this well of length L. So this is basically the nucleus. You know, the protons and the neutrons can't escape. The potential energy is infinity here. It's an infinity here. It's kind of like if you were in a room and the walls went up to infinity. You can never escape, right? Same thing here, okay? Infinity, and here the potential energy is 0 because there's no interaction between the protons and the neutrons, all right? So the potential energy is infinity, can't escape, 0, no interactions, infinity. I mean, you can't come up with anything much simpler than that, you know? So and here's the total energy. So in other words, a particle in this well will never have enough kinetic energy to escape, right? Because there's the energy, there's the total energy, the potential energy is infinity, you know? So there you go, all right? This is called the infinite potential well, right? Because it's a well, right? It's a well, and it goes to infinity, so it's the infinite potential well. We'll talk about the finite potential well later on. By the way, this is also the rigid box, the one-dimensional rigid box that we talked about in the previous chapter. Remember we, oh, you didn't supposed to see that yet? Remember we had a one-dimensional potential box, and we said that the electron acts like a wave, and the electron was was confined, and so we drew some wavelength, some diagrams, and we worked it out. It was a real famous experiment. So this is the same thing, but we're doing it in a completely different way. Okay, so I already said this, but I'll say it again. So this is all forbidden because you can't jump over infinite potential energy. So this is outside the box. Right here is inside the box. Right? This is the potential energy U. This is the total energy. So this is the kinetic energy, which is much less than the potential energy. Total energy forbidden outside the box. All right. So basically, we're going to do that. We'll do this one because it's the easiest one. We'll do that next. But let me just summarize. So when you're using the Schrodinger equation, all right, we're going to model atomic level situations with potential energy functions. And we'll then solve the Schrodinger equation. And we're going to find the allowed energies. Remember, energy is quantized. We'll find the allowed energies and the wave functions. And again, you want the wave function because when you operate on the wave function, you can find the kinetic energy. You square the wave function and normalize it. You can find out where the particle is, or the probability anyway, all sorts of things. So you got to find the wave function. It's like the x, in classical mechanics. Yeah, I just said this. All right. Once you find the wave function, you can determine everything, basically, right? So you got to find the wave function if you want to make any progress. Okay, so now we're going to do it. So now I hope you have your handout handy. Okay, so we're going to solve the Schrodinger equation. Now, most of you have not had a differential equations class. Don't worry about it. You'll do fine, but you're going to learn a few new things, I hope. Anyway, here's number one thing that you may not know. This is a second order differential equation. Whenever you have a second order differential equation, it means you're going to have two independent solutions. All right? So that's the first thing. Two independent solutions. All right, so here, just write them, So, all right, so the wave function, A and B are just coefficients. You can always have coefficients, right? So the wave function is A times psi1, that's one independent solution, plus B, another coefficient, times psi2. Okay, great. Whoopee. Right, so two independent solutions. Now, you may disagree with this, especially after today, but this is not a math class, it's a physics class. So these wave functions, they have to be physically acceptable. All right? That's the important thing. They have to be physically acceptable. So in order to make them physically acceptable, we impose what we call boundary conditions. So let's go through these boundary conditions. Okay, number one, the wave functions have to be continuous. Well, that kind of makes sense, right? I mean, the probability density is the wave function squared. Well, if you don't have a continuous function, what does that mean for the probability where there's no function? I mean, it doesn't make any sense. Okay, so you have to have continuous functions. Okay, fine. Number two, the wave functions have to be zero in regions where it is impossible for the particle to be located. Well, that makes sense too, right? That's basically this, because this is the probability density. Well, that's going to be zero, where it's impossible for the particle to be located. So that makes sense. Okay, wave function have to be zero where the particle can't be located. That makes sense. Number three, wave functions have to be zero at plus or minus infinity because we're doing our experiment here, not in plus or minus infinity. And four, we're going to always normalize our wave function. We talked about that last chapter, right? And just to remind you, this says that the particle has to be located somewhere between minus infinity and positive infinity. So this is the probability density, the probability per length, multiplied by a length. Well, the probability density is psi squared. So you integrate from minus infinity to positive infinity, psi squared has to equal 1. So we're going to do all that. All right, so the easiest example, the infinite well, okay? The particle in a rigid box, the infinite potential well, the model for the nucleus where there's no interactions whatsoever between the protons and the neutrons, and they can never escape because it's an infinite well. Okay, step number 1 is to identify the potential energy. So you have to use, whatever knowledge you have of physics or whatnot to identify this potential energy. And we already did that, right? So here's the picture. Now we have to write it in terms of mathematics. Well, that's not so bad. So U of x, the potential energy as a function of x, it equals 0. Okay, this is x greater than, this is x. It's 0 here, right? It's 0 here because there's no interactions. And then it's infinity outside the box. That's what we said, right? All right, so that's cool. And by the way, sometimes you'll do this, right? It's not going to be just one piece. It might be 2 pieces or 3 pieces or whatever. And that's okay. All right, so we've identified the potential energy. Bing, bing, bing. Okay, that's very nice. All right, so that's step 1, identifying the potential energy. Now we have to go through the boundary conditions, and this is where it gets mathematical. Okay, I'm going to do them in a different order. You'll see why. Okay, let's see. What? Hold on a second. Okay, so let's see. So wave functions have to be 0 in regions where it's physically impossible for the particle to be located. Okay, what does that mean? That means we're going to require the wave function to be 0 outside the box, right? That's what this says. The wave function is 0 over here, over there. Okay, so we're going to require that. You'll see. You'll see. And so this, we've actually killed 2 birds with 1 stone here, right? So this is satisfied as well as this, right? The wave functions must be 0 at plus or minus infinity because this includes plus or minus infinity. Okay, so we've done 2 and 3. Well, we haven't done them, but I mean, if we've written it down at least, we still have to do the work. Now we want the wave functions to be continuous. Okay, so the wave function is 0 outside the box. But it has to be, but then, we don't know what the wave function is going to be here, right? Inside the box. But we have to be continuous. So that means we're going to require the wave function to be 0 right there at 0. And it's going to be 0 right there at L. And then, of course, it's going to have to be, it's going to have to, whatever the wave function is, will have to come here too, right? So the wave function has to be 0 at 0 and at L because it's 0 here and here. So we want it to be continuous. I mean, it wouldn't make any sense, right? If the wave function were 0 right outside the box and then jumped over here or something crazy like that. And so this is just guaranteeing that the wave function is continuous. All right. Okay. Come on. All right. So now, let's do it. Okay. Okay, so we're only interested in this section. In this section, U is 0. So all we're going to do is we're going to put U equal to 0. So we just have d squared psi dx squared equals minus 2m over h bar squared E times psi, right? That's all we have. That's not so bad. Okay, so all we've done, again, we've just put U equal to 0. All right. Now, let's just do it. Let's just plug through it. So, d squared psi dx squared equals minus 2m squared. I'll put that E up there, I guess. Okay, so that's it, right? That's what we have left. D squared psi dx squared equals minus 2me over h bar squared times psi. I can do that if you want. All right, now we're going to make a little substitution, and I'll explain it in a minute or so. Let's substitute for this. Now look at 2me over h bar squared. That's positive, right? It's positive. So we want to indicate that it's positive. So what we're going to say beta squared is 2me over h bar squared. Now, why not just beta? Well, if you just say beta, it could be positive or negative, right? We're assuming reals, But if you say beta squared, then it has to be positive. Again, assuming reals, okay? So therefore, beta equals square root 2me over h bar. We'll get back to that, all right? But again, so we want this thing, we want to make it super obvious that this 2me over h bar squared is positive. That's why we call it beta squared. All right, so now we have d squared psi dx squared equals minus beta squared psi. Okay. Now, Physics 220 students, where have you seen that before? Or something similar? Simple harmonic motion, right? Simple harmonic motion was this, though. Right? Simple harmonic motion had a T. Right? All right. All I'm saying is, if you've taken 220, you've seen it before. All right, everybody else. Here's a differential equation. I've never had a differential equations class, Brother Weber. Tough. You can do it. So look at this. What does this say? It says you have some function, psi. You differentiate it once, you differentiate it twice. You get the same thing back, only with a minus sign and some number, some coefficient. So think back to your math classes. You've learned a lot of functions. I'll give you a hint. Trigonometry. Think back to your math classes. What function do you know when you differentiate it twice, you get a negative in some coefficient? What do you think? Well, I hope you all agree. Sines and cosines. Agree? Sines and cosines. Here, let's just prove it. Let's just do, let's do sine. All right? Sine alpha x, all right, where alpha is a number. So d psi dx equals alpha cosine alpha x, and d squared psi dx squared. What's the derivative of cosine? Minus sine. But then you're going to do chain rule, so you get minus alpha squared sine alpha x. So this compare that to that, right? What do we have? We have d squared psi dx squared, right? d squared psi dx squared equals minus constant psi, right? So sine is a solution. You could do the same thing with cosine and it also works out. So all I'm saying is that you don't need to have a differential equations class. If you just know basic calculus, you can solve the silly thing. Isn't that great? All right, so sines and cosines. Now remember, we have to have two solutions, right? Two solutions, two independent solutions. So we're going to say psi of x equals a sine beta x plus b cosine beta x. And you should prove to yourself that this works with that. But it does, I promise you. Okay, so there you go. Two independent solutions. Woohoo! Now, are we done? No. Because we have to figure out A, B, right? We've got to figure that stuff out. We've got to, impose our boundary conditions. So let's impose our boundary conditions. Okay, come on. Not yet. Oh, yeah, sorry. Oh, okay. Technical difficulties today. All right, so let's do it. So we want this to be true, right? So we want psi at 0 equals psi of L to be 0. Okay, piece of cake, let's do it. So we want psi we'll do the 0 first. Psi 0 equals A sine 0 plus B cosine 0. Well, sine of 0 is 0, so that's not a problem. But look, cosine of 0 is 1. Well, it's supposed to be 0, right? I mean, this is 0. But this, cosine of 0 is 1, so this is B, right? And this is supposed to be 0. Agree? So what does that tell you? Psi of 0 is supposed to be 0. No problem here, but that's B. So what does B have to be? So B has to be 0. Has to be. Okay? So now look at, we've gotten rid of half our solution, right? Goodbye. All right. So now we have this. Okay, so we've got rid of the half of it. Now let's do this. And some of you may have never seen this, so pay attention. So psi at x equals L equals A sine beta L. And again, that has to be 0, right? That's the boundary condition. It has to be 0. Well, where is sine equal to 0? 0, pi, 2 pi, 3 pi, right? All that. Okay? So this implies that beta L has to equal n pi. Okay? Now, we're going to say that n equals 1, 2, 3. We're not going to say 0, though. Why aren't we going to say 0? Well, because if n were 0, what would that mean beta L is? 0. And if beta is 0, that means E is 0, right? And if E is 0, the velocity is 0. And what do you learn by the Heisenberg uncertainty principle? You can't say that V is 0, right? There's an uncertainty in V, right? Remember? Heisenberg uncertainty principle. So we're going to say n is 1, 2, 3, blah, 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 on and on and on. Okay? I got to do it. So therefore, beta equals n pi over L. Okay? So beta is n pi over L. So therefore, what is our wave function? So therefore, our wave function is A sine beta x. So n pi x over L. Well, we're getting there, right? We're getting there. I mean, we still have to find A, though, right? We got to normalize the function. But we're getting there. We're making great progress. Now, before we do that, I want to just point out something that's important. It basically explains why we did this beta squared business. Okay, so up here, and also over there, but I just erased it. So I had beta L equals n pi, where n is 1, 2, 3, on and on and on. And then we have over here that beta is 2me square root over h bar squared. Oops, over h bar, that's right. Okay, so this is beta, and here we have beta is n pi over L. Agree? So here we have our beta, and here beta is n pi over L. So square both sides, 2me over h bar squared equals n squared pi squared over L squared. And then multiply both sides by h bar squared, divide by 2m. And h bar, okay, what's h bar? H bar is h over 2 pi. We square that, right? So we have so pi squared kills this pi squared. Then we have 2 squared, which is 4, times 2, which is 8. And so what are we going to get? We're going to get n squared. Let's just pull it out like we always do. H squared over 8ml squared. So that's E. Call it En. So wow, what did we just do? We just quantized energy again, right? Okay, so if we call this E1, look at h squared over 8ml squared. then E is equal to n squared times that. So once again, only certain values of energy are allowed. We quantized energy. Now, where have you seen that equation before? Remember, I told you that this was the one-dimensional particle in a box, which we did a while ago. Well, ta-da, right? When we did this a while ago, all we did was we confined, the de Broglie wavelength, right? We had the exact same equation, Well, of course! I mean, it's the same problem. It's just that this way, we didn't know anything about the Schrodinger equation. We just used the fact that the de Broglie wave had to fit in here, Well, here now we're solving the Schrodinger equation. So it's kind of nice, though, that we get the same equation. I mean, it better be that way or it's all garbage, right? Okay, so we're doing great. All right, so we quantize energy. Nice. But, we still have to solve, we're going to normalize the wave function, right? We've got to normalize the wave function. Okay, let's do it. So let's do it. Yeah, let's do it. All right. Let's see. I got to write this down somewhere. So now we're going to see who learned their calculus. All right, so there is our wave function, and we have to normalize it. So here is the normalization condition, right? It just says that the particle is somewhere. The probability that the particle is somewhere is 1. So let's go. So we want integral minus infinity to infinity psi x squared. And that, what is that equal to? Well, that's equal to, now look at, do we have to really go from minus infinity to infinity? No, because the wave function is 0, except, outside the box. So we just really need to go from 0 to L. So 0 to L, and then what's the wave function squared? That's that thing squared. So we can, that's a coefficient pull outside. So we get a squared sine squared n pi x over L dx. Okay, now there's kind of a problem. How do you integrate sine squared? Well, you look it up, right? You look up integral tables. You use integral tables because this is a mess. And, okay, so we're going to just look at the integral table. So I assume you've all been exposed to an integral table. If you haven't been, well, welcome, all right? So just look this up. I mean, in the olden days, they would print books. You just have all these integrals, these horrible integrals. But some easy ones, too. Nowadays, they have this on the web. So integral sine squared ax. So a is just some coefficient, right? Some number equals x over 2 minus da. All right. Now ours is a definite integral, so we don't have that. Okay. So for us, n pi over L is the a. Agree? Right? Because it's the coefficient here. So for us, I'm going to say a is equal to n pi over L. All right, so here you go. Let's do it. Should have written up here. All right, wait a minute. All right, so let's just do it. So we have our a squared. Okay, now we're just going to use what we have. So x over 2, okay. By the way, we can put a little n here because we know we're going to have quantized states, so why not, right? Okay, so x over 2, then minus 1 over 4a. Now, our a is n pi over L, so we're going to flip it, divide by 4. So we're going to have minus, so we're going to flip it, so we get L over n pi, but then we're going to put that 4 there. All right, so then a sine, then 2ax, so we multiply that by 2. So 2n pi x over L. And then we integrate it between 0 and L. So we're going to use this again. I mean, don't memorize it, but write it down somewhere so you can refer to it. All right, you ready? Let's do it. So then we have an squared. So we put in our L over 2 minus L over 4n pi sine 2n pi L, right? We're putting L for the x over L. And then minus, then just put in 0. So 0 over 2 is 0. Then you put a 0 here. Sine of 0 is 0, so it's just 0. All right. Okay, now hold it. We're not done yet. An squared. Okay, L over 2. Now what's this? So here the L kills the L. The n is an integer. So this is sine 2 pi, 4 pi, 6 pi, and what's all that? 0. So this goes away. So we're just left with that. Yeah. And again, this equals 1, right? Somewhere I'm supposed to write that. So this is equal to 1. So therefore, what does an equal? So an squared equals 2 over L. So an is just the square root of 2 over L. Yes. All righty. So now so there you go. So, all right. So this wave function, it's normalized. It satisfies all the boundary conditions, and it satisfies, well, more, let me start over. It satisfies the potential energy function. It satisfies all the boundary conditions, and it's normalized. So there you go. Well, but there's more to it. Sorry. I mean, that's the wave function inside the well. Well, how about outside the well? We already did that, right? So this is how you have to write it. You just say that the wave function, oh, by the way, sorry. Remember, the wave function had to be 0 at x equals 0 and at x equals L. Let's see if we satisfied that. We did. Well, let's see. Because if you put in a 0 here, you get sine of 0. Sine of 0 is 0, so this is 0. If you put in L, you get sine n pi, which is 0, so it works. Okay? All right, so the wave function is 0 outside the box, less than x, greater than x. The wave function is 0 at the edges of the box. I just said that, at x equals 0 and at x equals L. The wave function is 0 at plus or minus infinity because it's 0 outside the box. And here, inside the box, here it is, right there, this part. Okay, so that's how I have to write it, 3 parts. All right, now let's kind of assess this or summarize it. Okay, number 1, we quantized energy. And we got the same result as before, right? So this is the infinite well where the particle is stuck. It's a confined particle, one-dimensional confined particle. Particle in a box, infinite well. Quantized energy. Number 2, you know, this wave function depends on n. That's why it's a good idea to put a little n here. So we have just stationary states, right? We only have certain states that work. Now, you know, we could draw these things, right? I mean, we can draw sine curves all day long. So let's do it. I'll have the computer do it. So there you go. All right. So just put it in. Just put n equals 1. By the way, this is 2 graphs in one. Let's just concentrate on the wave functions first. So if you put n equals 1, you get sine pi x over L, and you go between 0 and L, so you just get this. So that's psi 1. If you put 2, you get the whole wave function. If you have 3, you get this, right? So you see a pattern, right? So psi 1 has like 1 hump, psi 2, 2 humps, psi 3, 3 humps. Okay, so those are the wave functions. Now the energy, remember, En En equals n squared E1. So this is the energy, right, on this side. And so E1 is whatever, right? Here's n equals 1. This is E1. The next would be the 2 state, but the energy is n squared E1. So E2 is 4E1, so there it is. And then the next one is n equals 3, so 3 squared is 9. So E3 is 9E1. All right? So this shows the energies and the wave functions. That's kind of cool. All right, and then when we square the wave function, we get the probability density. Well, that's, if we can plot the wave function, we can certainly plot the wave function squared, right? So here's psi1 squared, psi2 squared, right? So this hump, and here you get 1 hump, 2 humps, 3 humps, right? Okay? So there's the probability densities in the green there. So there you go. Now, and there's more, but this is enough for now. Okay, let's consider this one. Again, remember, this is the probability density, px, right? Because px, probability per length, multiplied by length is probability, which is the area under the curve, which is just a number. Okay, so look at this graph. Where's the particle most likely to be found? Well, it's kind of obvious, right? Right there at L over 2. Okay, look at this graph. Where's the particle most likely to be found? Oh, right there and right there, right? So L over 4 and 3L over 4. Okay, right. How about that one? So it's going to be L over 6, 3L over 6, or L over 2, and 5L over 6. All right, that's fine. Now, wait a second. Look at that one. What's the probability, look at just the 2 state. What's the probability that the particle is located at L over 2? 0. Well, please explain. If that's true, how does it go from here to here? I mean, if it can't be there, how does it go from there to there? So, maybe this model isn't so great, right? All right, so anyway, so we've solved the Schrodinger equation, and we're going to do some examples with it next, but this is a good time to quit. Let's quit.